the show on the road. So it's my pleasure to welcome Dr. Pablo Sobron from Impossible Sensing to give the colloquium today. Pablo is not new to our university. He did his postdoc here just across the pathway there in Earth and Planetary Sciences, following on getting his graduate degree in 2008 from the University of Valladolid. I may be trying to get the pronunciation right there, but it's perfect. Following the postdoc, a couple of years after that, he founded Impossible Sensing in order to pursue turning fundamental physics into applications for exploring our planet and others. And so that will be the topic today. Oh, please, take it away.
Thanks, Eric. Thanks, everybody, for being here today. Also, the ones online. I don't know how many we have, but probably it's a good number. So, yeah, so, double special time for me. As Eric said, I spent a couple of, maybe 3 years here as a postdoc, and beyond making a lot of friends, a lot of whom I see here today, which is good. I also did develop certain skills and certain knowledge of what I did not want to do with my career, right? And I was one of those who I loved academia and I had a blast working here, but I realized that I didn't quite want to be limited by grant cycles or internal directions given by university on what to do, what not. I really wanted to push the limits of building sensors, of applying the physics knowledge that I have to really do something meaningful, something applied. Not for other reason than it's because I care about. I mean, I really believe and I love fundamental research. I use it every day, believe it or not. But I really also find a lot of pleasure in really solving problems in the real world and applying this deep knowledge into solutions that really help everybody. So what you're going to hear today is a talk probably very different than what you hear typically. I'm not going to show you my last paper or my last grant or any equations or any theories that I have. I'm going to show you a little bit how to turn a chaotic brain, like all of yours and mine, into an idea, right? And make that idea be of value to some customers or stakeholders, call it whatever you want. At the end of the day, what really matters is somebody doing something with what you're creating. Is there any use, or is there any advance that you're putting forward by working your theory on your new sensor, on your new big balloon in the sky, whatever it is? What matters is, is it really, what do you get out of that, right? As the creator of this technology. And I think, when you look deeper into your brain, and you always are playing into different fields like this, and this is not new to anybody, but I think I like this plot, and I use it quite a bit, just to really show that, yeah, we all live in a very chaotic way. We all live in a place where we're really pulled by many directions. But at the end of the day, you can harness all of that and really capture that and make an idea happen, the way you want it. And if you're like me, and some of you are probably my age, I'm sure, you learn that there is a very big disconnect, and there is a no cross line between physics, the basic Blackboard physics, equation theory, deep thinking, almost philosophy, and what is the applied world, the applied physics or engineering, right? And I did learn that the hard way, and I started working in physics. Actually, I got my PhD in physics, as a matter of fact, but I never quite got to use it in the sense that I studied my studies for. I was working on thermodynamics in physical chemistry, actually. And I was looking at how certain metabolism, certain bacteria harness chemical disequilibrium and use that to oxidize iron, reduce sulfur, and create conditions that we thought were inhospitable, conditions that we thought that no life could exist, like high acidity or very high temperature. Turns out that Mars had those conditions in the past. So suddenly my PhD became a race to, hey, I know these systems. We know that there's water on Mars. And how do we actually try to draw the line, the connection between what water that we have today and 2 billion years ago water out on Mars? So I started to really realize that to be able to explore Mars, it wasn't going to be enough to really understand thermodynamics or physical chemistry. It was about to send in a lab to Mars that can actually explore the planet and tell us what Mars is made of, A, and what Mars was made of in the past, right? And is there any connection with life today on Earth, as we know it, and potential for Genesis 2.0 of life out on Mars? So that's where I started to understand that this divide between basic physics or your paper and pencil physics and the applied physics is not such a divide. There's a continuum in between, and there's something that is now called deep tech. So you probably heard about this before. In a very simplistic way, deep tech is where engineering meets scientific discovery, right? And this is the place where you put forward radical engineering that is substantiated by very scientifically important and pioneering results and discoveries. So in essence, it's the kind of developments that really create opportunities for extreme growth in whatever field you want. I'm not talking about economic growth, but the growing capabilities of doing new things. Create expectations to really do things that are really, really important for the world. So this is the place that I sort of saw myself happiest at. I'll go into that later, maybe at the end. But what I wanted to maybe bring here, and I'm very happy that there's a lot of students or postdocs or both here in early career people, because I think, you know, as you navigate the job market soon or your next career move, I think there is a place here for everybody that has deep understanding of scientific phenomena, that have discovered some scientific breakthroughs, or have understood discoveries from other people and found a way to make them into a product, into something useful that can be taken to the next level. And this doesn't need to happen today or tomorrow. It's okay, and it happens all the time, where you take an idea from science, and it takes 10, 15 years to become a reality in engineering. Think about any Mars mission or any, James Webb Telescope. The time it takes from when you propose the thing to NASA till it's actually flying, if it's flying at all. So time is not the problem here. The problem is this mental construct that we have that, we have to compartmentalize disciplines in a way that that's not helping many people. So what we do in impossible sensing is really harness all these things and really deep dive into this deep tech here from St. Louis. I chose St. Louis for a place for the company for many reasons. And one of them is that I have created a network of friends and colleagues here at WashU through my time here that I thought was very unique in many ways. And we can go that at the end if you want on why specifically is so special about St. Louis. But for once is that it is a place where we don't lack talent in the fields that I care about, space, climate. We don't lack resources in terms of people driving change at the corporate level specifically, and also academic level. Obviously, WashU, SLU, and other universities in the region are pioneers in many fields that are important. But I found that this is a place where really the creativity that I could harness in the city, talent, and the cost of life here was the perfect spot to do something important. And this is one of the reasons why we're here. We do have offices and spin-offs, California and in Canada and in Europe as of next year. And hopefully, thanks to the efforts of Jeff, whatever it is, Jeff, and Brad Jolliffe at EPS, hopefully in a few years we'll have an outpost in the moon on a combined WashU impossible sensing mission to the moon. But while we get there, the things that we do span everywhere from deep space to deep ocean. So we found over the last few years, and this is the classic startup tale where you're really setting in motion a wheel that you don't know where it's going, but you know you have to bring in people to help you move it, start the flywheel. And you don't even know what customers want. You think you have something very important in your mind, something that you really are passionate about. In my case, it was a new way of doing Raman Spectroscopy, and I'll talk maybe about that later. But I did feel that there could be something useful for that beyond what I have been doing traditionally with NASA and other agencies. So essentially started talking to other people randomly at conferences, using the network of my supervisors. So this is an advice for students. Leverage everybody who your supervisors know, because those people will teach you things that may be useful for you. And learn that at the very end of the day, what people want, what people really care about is measuring things. If you have a process, you have a field, any application that requires getting intelligence, information, knowledge, insights from a process, you need to make this way faster than you can do it today, more sensitive, and in a way that doesn't involve a lot of resources to process information to make a decision. So in other words, we're in a place in time where at the edge computing, the art of getting insights far away from centralized control in the field where it matters is what creates value today for everybody, from NASA to farmers 10 miles from here, to agencies looking for resources in the seafloor, to oil and gas companies, to offshore wind. Anything you can imagine needs this way of sensing. So there's no doubt that you guys know this, since the quantum center and the quantum sensor group here has that in mind. There is a need for sensors, better sensors. So let's build them. So we are building them for applications that I said before go anywhere from the deep sea to deep space. And one of the things that I'm most proud of is the connection that we've made, and I guess from the beginning, with this university. And we have now five full-time engineers. It's 4 plus 1 data scientist, who most of you probably know, Daniel. Hopefully he's listening somewhere. So we have 5 full-time staff that come straight from here. And I think that's been a very, very fruitful relationship between this university and us, by which we leverage the amazing knowledge that this university is giving to people and to grow our business. But we also give WashU an opportunity to say, hey, we are bringing talent to the city and they're staying here now, right? As opposed to going to the Bay Area or Boston or whatever people go these days. So beyond that, we've had a cohort of interns. I'm sure I'm forgetting some of them, so apologize if you're listening, your name is not here. We keep getting interns all the time. So we had a number of interns running through our lab. And one thing that I'm proud of is that they are now our best ambassadors. They come to their partners, to their peers, their friends. They'll tell them how amazing it is to work on Impossible. And it's not something that happens every day, I think, for companies. Of course, we pay, but it's not about the pay. It's about the feeling that people have that are doing something important. So something like 3, if not more, projects that we actually have together with WashU right now. And I'm only listing here 3 that are linked to moon work that we're doing in the future. And I'll show you pictures of what these instruments look like. But here, the idea is that, as you know, St. Louis region has a very strong heritage on moon exploration. I mean, it's not an exaggeration to say that St. Louis initiated the race for humans in space. It all started here. Gemini program was built here. NASA was testing spacecraft here. People were training here. And I think more people don't know this in the city anymore, but I think this is one of the capitals of aerospace, at least in the last decades. But in parallel, WashU in particular developed one of the, I'm going to say, top 5, if not top 3 departments of space sciences, anchored by some of the best professors and minds on Moon and Mars science that we have in this country. So coming with this together, we find that that scientific and legacy, plus now our innovative approach to developing technologies, makes this connection one of a kind. There's a question.
What do you actually do?
Care to stay for a few minutes more and that's okay. What we are pushing the boundaries on is photonics. So the science of harnessing light in matter interactions, and also fusing that with data science. So we are not only investigating how to utilize photons in a way that is useful, but also giving that usefulness to our users in the end. So there's four particular fields where we are pushing and building new optical sensors, and these are anchored by these 4 phenomena here. And you all know more about this phenomena than I do, so I'm not going to explain any of that in detail. But I'm going to show you some of the things that we build that utilize this phenomena, and how do we actually use it to build this instrument. So again, we're not focused so much in developing new theories, like here. We're not focused on really learning the in and outs of the physical phenomena. That's why we have universities like this one here. We are interested in how do we utilize what's important about this phenomena to build instruments that are useful. Okay, so when you, from the Blackboard to what really is important for us is that, oh, hey, when light hits matter, on the other end, you're seeing light that is in different color. There is some energy loss, energy gain. Can we measure this energy gain and loss to really acquire knowledge about our samples? So, so this is the very first Raman spectrograph that was made almost 100 years ago. And believe it or not, the highest end Raman instruments that are built today are now back to this same design from the original one. Now we use lasers instead of the sun, but it's essentially the same system. So we still use well, I guess blackboards or whiteboards, and we also build instruments that look like that very much. So this will not be the first Raman instrument built or the first Raman spectrometer spectra generated, but this is the very first Raman spectrograph that we built in-house that is using a new way of collecting light that you'll see later in a few slides ahead. So actually, we also make plaques like that one. So this is hanging in our lab, and this really, I mean, not gonna read all that, but this marked a milestone in our company that really helped us go to NASA and say, hey, now this is ready to fly, right? So so now we're getting calls from NASA saying, hey, what can you do with this? Can you tweak it to measure life on Mars, for example, or Europa in future when we go there? So so we're not doing things that are not dissimilar to what we were doing 100 years ago. Only now we actually apply them in many applications, like you'll see after. So another technique that we utilize here a lot, and I threw this plot here. Some of them, now the Saha Boltzmann plots, of course, better than I. Here, what we do is we actually crank up power of laser, and we break down matter. We make plasma expand, and we're looking at the emission from the plasma. So nothing new here. What's important here is that we're now shrinking the size of your typical LIBS instrument into something that you can actually take to Mars or the moon, or maybe a couple hundred miles out of here to take a nice photo shoot. But the important thing is that, again, it's about when you think about future astronauts going to space, what they need is something that they can use quickly, they can use robustly, they can trust to give information about what the moon or whatever it is they're going to is made of in a way that fits the job. Which for NASA is, let's find resources on the moon, but again, let's find perhaps organics on Mars and maybe life. Another of the techniques is fluorescence. So in this case, this is much better known technique and understood technology as well. Is the art of absorbing a photon and then emitting it in different wavelengths. And that shift, of course, tells you about what the matter is made of. And one thing that we well, not us only, but of course, very highly visually impactful fluorescence maps that tells you about spatial distribution of molecules. And some people call it art. And as a matter of fact, if you have time between now and November 10, I think, we have a show at a local gallery. Believe it or not, we're showing now science as art that we call low gravity. And what we did is basically print out real scientific products. This is a paper we're writing right now that we are actually looking down into the microscopic distribution of carbon in soil, and we're taking fluorescence pictures of that, and we're just blowing them up and seeing the distribution of these organic tracers that we can use with NASA now to look for life on other planets, but also make art. So if you like art, you like science, I think this is the place to be for the next couple of weeks. But jokes aside, I think one of the things that we find that I didn't know when I was in school is that there is many more vehicles to explain your science than papers and conferences have to expect. So it's fine to do that, and it's great. This is the way it should be communicated. But to the real public, to the people who pay taxes to really get your grants and to get paid, I feel we have a duty to communicate things in the way that they feel excited about. And we find that art is one of those vehicles that are underutilized by scientists to really show the power of the work we do and why it's important. So we do things like this on occasion when we have something that we think is important to communicate and in a good way. So a lot of you will recognize this skyline. So LiDAR is a reflection technique. Well, there's many ways of doing LiDAR, but the elastic reflection of light, so you shoot a photon and it just comes back to you, is what people use and everybody uses now to do very, very high resolution renders for cloud points of things, especially. And so this is a real LiDAR taken of St. Louis by the USGS. And I think we're using this now to really develop the next generation satellites that now can shrink the size of a LiDAR system by about 20 times. So a LiDAR system today in ISAT-2, this is NASA satellite, the best climate satellite that we have right now. The LiDAR is the size of a small car. And it has to fly on a spacecraft the size of half this room. So that's a multi-billion mission, multi-billion-dollar mission that actually is running out of fuel in 2 years. ESA has the same problem. Their mission, its name slipped my mind right now, is running out of fuel as well. So in about 2 years, we stop having global LiDAR coverage of the world. So we stop having global data on ice sheet, elevation, forest canopy, other atmospheric phenomena. We'll have some data from aircraft and other satellites, but the global scientific good data that only these two missions can provide will blind for the next few years until the next generation satellites come in. So the innovation that we're doing here is when we're shrinking the size of these LiDAR systems to the point that they can be deployed in small satellites. So you guys have flown things in balloons and other vehicles here, and you know that every gram counts, right? So we think that if everything goes right, in a few years we'll have the first demonstration of this system that can do the same LiDAR as we do today with big satellites, but in a small form factor. So now you can fly it in small sats, and you can provide global coverage as well at a much lower cost, which will provide the data that we need to really start monitoring and develop policies to combat climate change. And so now I have a few slides that talk about instruments and things like that, but I think I'll go very fast because I wanna spend some time in the last few slides that really probably are more value for most people here in the room and online. So things that we do with our innovations, right, is enable things like measuring molecules on the clouds of Venus, and hopefully with this system that combines Raman and fluorescence in a long tether, and can actually get the chemistry of the clouds of Venus, which we think contains organics that trap UV light from the sun. And those organics maybe will be tied to life. We don't know yet. There is missions to Venus coming up in the next in this decade. We hope that one of these missions eventually can fly one of these systems to really look for trace organics in the clouds by using fibers and other experiments. So I'm gonna go quickly here. You probably have my email from the list here. If you have any question about any of this, shoot me an email, find me on LinkedIn, and I'll be happy to explain more on that. This is the instrument that I showed earlier, the plaque that we have, our first Raman. So here, when I said that we went back to what Raman did before, 100 years ago, I'm not kidding. So back then, what he had was just telescope getting light. He had a prism, had a sample, liquid sample through which light went through. Then he had a prism, and then he had mounted the prism on a rotating stage. So manually, somebody had to be changing the stage, shoot light into a silver film that was moving as well. So it was collecting light in time that was shifted in energy because of the Raman effect. So of course, times have changed, and then with CCD developments, we move away from all these moving parts and have one snapshot with all the photons in one frame. The problem with that is that we saw that CCDs are not very sensitive. So the new requirements of industry and of course NASA are that you need to measure things very sensitive. So now we took an innovation that is not ours, of course. This is Texas Instruments digital. They have multiple names, but one of the names is MEMS, Microelectromirror systems, and that's exactly what you have here in the projectors. This is arrays of millions of micromirrors, about 10 microns across, that you can flip on on demand, and that way you can steer light into different places, especially. So what we did is we thought, well, the same way you can project a movie out, how about you project light from your sample back into the detector, right? So somehow nobody had that idea before, I don't think, and we got NASA to really buy into this and build now a ready-to-fly instrument that actually uses these mirrors to make masks that we're using here. And here you can see what the photomultiplier is seeing in the CCD, these 4 squares right there. So when you turn some mirrors, you're seeing different chemicals, right? And you can quantify that because you know exactly how many photons you're counting with the photomultiplier. So we're back to the dispersion light, monochromator kind of thing situation, but now it's way more sensitive than when obviously 100 years ago, Raman were doing things. So this is some of the things that we really do and we build and how we build it, right? So one thing that I tell all my engineers, and I say, hey, let's engineer when we have to engineer. If there is off-the-shelf technologies, if there is scientific discoveries there, let's take it. We don't have to reinvent the wheel every single time, but let's be smart about how do we put together everything that creates something novel, something new, something useful again. And for example, case in point is this is the LiDAR system that I was telling you before. that now is able to use the same technology, the same micromirrors, to steer your LiDAR as you're moving on top of your sample. So you can fly faster from closer to Earth, but you can still spend enough time on top of your sample because you're moving to collect enough photons to enable your measurements. And that's what allows us to minimize or reduce the telescope size from 1 meter to about a third of that to get the same light, because we're spending more time because we can move the laser now by using this technology. So we can measure things like we used to see here before. That's the aspirational measurements that we hopefully will do soon. But the idea is to really replace all these massive, costly one-off LiDARs by a stock system that you can fly small sats cheaply. This is another of our Raman instruments. This one is called Merlin. And here we actually built the very first prototype in collaboration with WashU, with the engineering department, experts in surface enhanced Raman spectroscopy. And what we're doing here is we're building a plasmonic window. It's a window that we etch and then we sprinkle with gold nanoparticles or silver. And what happens is that when the sample gets thrown into this plasmonic window, the Raman effect is amplified by probably 10 to the 6, something like that. So you start seeing things that you couldn't see before. Sensitivity enhances accordingly. So now we gave this to NASA to do lab work to look for trace organics on Atacama soil and Antarctica soils that are very, very life poor, and it works. So now we can do part per billion Raman analysis on samples using a pretty simple, small, compact system that eventually we can fly to other planets. So again, we didn't invent Raman or CERS. We just found a way to put it together in a way that enables these measurements that you could never do before. And that's kind of the art of the things that we do. Another of these ideas was that, when you have a probe, right, that you want to focus to get your measurements, because for the most part, you always want to be at the same distance from your sample so that you can get your data right? So the problem with that is that typically you use actuators, so you use mechanical mounts like your, DSLR camera, and eventually over time, especially in space, those systems stop working well. You miss steps, you miscalibrate, and then you really don't get the science that you want. So we found a way to combine liquid lenses with MEMS mirrors, similar to those that I mentioned before from projectors, but in a way that you can actually now do 2D mapping, and you're always on focus without having to move any single mass. So just by playing with this adaptive optics, we can now do this, what I call 2.5D mapping. So we can map a surface in 2D, but we can follow topography if there's any. And there's a lot of value in that, as you'll see in the next couple of instruments. This one I showed earlier, so this is just a LIPS instrument, but it's small enough and good enough, this is the difference, compared to commercial handhelds that actually can be used now for future human exploration. So this is an instrument that we're building with Korean space program for the future moon efforts as well. So the astronauts probably won't look as cool as these ones, but probably we're doing the same thing on the moon this decade, hopefully. So this is one of the agricultural applications that we're developing. So here what we did is we stuck together a micro lens array on top of a CMOS detector so that we can actually filter out information that is useful. So, when we talk to the customer, and actually this is the Department of Energy funding, talk to them and say, hey, everybody talks about, getting infrared data, fluorescence data, whatnot in the field. Here is what we think is important, or we know is important when we talk to the customers. And it's these three things, right? Freshness of the soil, how humid it is, and is there any organic matter? Is there carbon there, right? So what we did is, let's just build a video camera that you can basically move around in a robot like this, and you can just scan the soil as you're moving. So it's just similar as your photo camera from your cell phone video, but now with a filter that tells you exactly what you care about, these three things. And yeah, so we tested it last week in Kansas with this vehicle, and now we can do automated mapping of soil on the surface for now. Future will be underground for these particular parameters. So again, what's the value or what's the innovation in putting lenses between cameras and your object? But there's not much there. What it is much is that we actually did it in a way that delivers these three things that people care about. And I think that's kind of the cool part about this instrument. It really does the job that is needed. And somehow nobody did before. Similar to that instrument is this one that was built by Alian Wong, next building, EPS. And here she's been working on this for 10 years plus. And she's been able to shrink the size of your classic near infrared reflectance sensors to the size of basically a cell phone, a little thicker, less than ½ kilo. And we can actually now measure water content, minerals on other planets. So this is one of the instruments that, together with Jeff and Brad, we're proposing to fly to the moon in 2024, 2025, to look for water and other minerals on the moon. So this is, again, next door, almost ready to fly. And same as this one. This one actually is also ready to fly, and this one does mapping, LIBS, Raman, Fluorescence. This combines everything. This is the one Swiss Army knife tool that can actually do what you could never do before in other planets. So we have never gotten any core until a few months ago on any planet, and this is the Mars 2020 mission. Now it's getting cores from underground into a cache. They're gonna come back to Earth hopefully this decade. We'll see. So what we're telling NASA that we think we should do, and they agreed for now, is that, well, let's look at the core as it's coming out instead of waiting for it to come down to Earth and waiting, in case it doesn't even come back. Let's take it out, and as it's coming out, let's use our adaptive laser and optics to really scan the core, looking for things that are important right there in situ. So this is what we have now. It's almost ready to fly, hopefully this decade too, getting core analysis done. And this one is called Periscope because sometimes you don't want a core, you just want to make a hole and drop the probe here. So this one is using fluorescence as well. And here you see the same pattern of pictures or photos or images that are actually a combination of different properties of the ground, particularly life, typically organics that are life related. So in case there's no core, now we can actually just drill a hole and deploy the tool down. And this one is also one that we're building together with EPS here. This one is to bring sensors into the drill. So think about when you're drilling in the wall with your Dremel or your tool. Now this one will have a little sensor that is telling you what your wall is made of. I don't think that's important for you in your wall. It's not important for my house, but for NASA, when you're looking for water on the moon or other things, very important to really look at what's under without having to get sample up, right? So this is an in situ subsurface tool that uses LIBS to look at chemicals while you're drilling, real-time chemical profiling. So we have funding from NASA for this. This one is for underwater. So this one is one of our favorite projects because that will eventually bring lasers like this one you see here down into the ocean. And the idea here is to expand it, and now we have funding from other agencies to build that into an underwater vehicle. So the idea here is to incorporate all these, most of the things that you've seen before in this last 20 minutes, optics, lasers, detectors, into a package that we can plug into an underwater vehicle that can autonomously scan the seafloor on Earth first to look for things like rare earths, critical minerals, new communities that are in places that we don't know of, so that when we start thinking about mining the seafloor, we can do it in a sustainable way, because we're looking at both things now. Biology and minerals, now with mobile platforms, the way that it's not done yet before. So hopefully we keep working on this for a long time and it works the way we want. That's one of our favorite applications. For the moon mission that I mentioned earlier before, together with WashU, we're building this lift system. You see it there. Actually, right now it's here, in this building. We're doing tests with Jeff's chamber, vacuum testing. So the idea is to fly it on a small rover on the moon in 4 years and just shoot at rocks and look for water and look for minerals. The idea here is to start thinking about the moon as a resource. So future mining of the moon will happen, and this tool can actually tell us what the moon is made of in a particular landing site at the scale that we need to think about future mining. And just to finish all this, and one of the big problems that we came across a couple of years ago is that, hey, we have this cool tech. It's getting so much data. It's amazing. Now, how do you transfer 1 gigabyte from one sample from Mars to Earth? The answer is you don't. There's really no bandwidth that allows you to really transfer all the information that you need back to Earth, right? So this is again the problem of then we should just be doing the science on Mars and not on Earth, right? So can we build intelligence into our sensors that can handle this data volume and only send back to Earth the data that we care about, which is probably how much calcium do we have in this rock? Is there any volatiles here? Is there any organics, any water? Things like that we can get from this data, from these maps, but you need to build the technology to do that there. So this is work by our own physics own Daniel Van Hoosen, who is working on a new algorithm here he calls DREAM to really enable this. And in essence, what this is all about is measure as best as you can, downsample, get rid of the things that you don't care about, don't matter, and send only that to Earth. Okay. Now on the Earth side, you're gonna get it back, right? And this is the key, right? So you need to reconstruct that information, decompress it if you want, to make it something useful that actually you can do here on Earth with. And this could be the whole set of sample or small set. That's what Daniel is working on. And what he found is that this is still in progress, and I think he can probably be happy to give a talk here on this, of his experience on how applying what he learned here into real world applications. He's working with different neural networks systems, auto-encoding platforms to really understand, of all the data that we have, do we need to connect everything with everything, or can we slowly, select features that are important? And that's what we use to really drive the engine to get the data that we need, right? So this is work in progress, and I will defer to him if he feels like giving a talk here or he's invited to really explain this. But I think this is amazing research that is now enabling this this field of at-the-edge computing that we are entering. So I want to finish with, well, I call it wisdom, but call it whatever you want. But one thing that I was very happy to see today is that I've gotten questions from faculty and postdocs and grad students on, hey, I really want to keep working on this. I want to move to industry. I want to keep doing research. How can I do it in a setting that has resources, has application, makes money, and actually fulfills my need or my desire to maybe stay here, right? Or so the one thing that I'm happy that I got those questions, because I really was prepared for this. And the one thing that I found through my years of working with startups, mine and others, working with government, working with academia, is that the only people that really succeed, people that really make an impact the way they want it, is people who really do what they really care about, the things that you are deeply passionate about. And right now you're lucky that you live in a world where if you need a job, you'll find a job. We can hire people fast enough in industry right now. We're seeing a shift in what people care about. For the last 40 years, it's been security. I want to have a good job, stable, well paid, easy, build a family, build my life, retire and be happy, right? We're seeing that shift now that people are really caring about other things, right? Climate change, values, corporate citizenship, the things that really, really you care about, that you want to make an impact in the world, you want to see that reflected in the company or the place you want to work with. So right now is actually a great time to really stand your ground and really only take jobs, only do things that you really are passionate about. I think that's my first advice that I have for you guys. All of you here are highly educated individuals. You've developed expertise in your field. Nobody knows more than you in your field. Students and of course faculty. You found that, right? Or you're finding that. So stick to that. It's okay to change directions. It's okay to change jobs. But I think you'll find that it's much better to be happy and to follow your passion if you really keep doing or focus on what you're the best in the world at. And more than anything, at the end is learn what makes you really happy. Is it money? Great. Is it saving the world? Fantastic. Is it working 2 hours a day? Spectacular. Yes. Find what really makes you happy. And if you are lucky enough to find the intersection of these three things, right? What you really care about, what you're the best at, or can be the best at, and what really makes you happy, what drives your internal passion, I think that's the place you need to be. And again, I wish I was I was your age now. Things are different when I finished my grad school. The economy was collapsing. Eric can attest to that. I think we finished PhD at the same time. It was tough times to really even get a postdoc because nobody had grants anymore. So right now it's the opposite, right? There's a lot of money to be invested in both government research, academia, definitely industry. And I think now you are at the unique place to really harness all of these things, find what you want to do, and just go do it. And that's all you need to do. So I will stop here, Eric. I think give 10-15 minutes of time to do any Q&A on whatever topic you want. And otherwise, find me an email or LinkedIn, and I'm happy to answer any other questions.
Time for questions. Anyone online, just unmute and speak up.
I'm wondering if the university had like $20 or $50 million, could they do something to make it easy for graduate students to start startups?
The $20 million question. So WashU has I don't know the name official, but it's an incubator program whereby they provide legal support for PIs, faculty, and postdocs for students to really launch a company. I do not know how it works very well, but I know it's not enough. I know it's not enough because I don't see many companies spun out of Washington University in other fields than medical research or bio or life sciences, let's put it that way. One thing that I would love to see more is more science-based or engineering-based companies spinning off of this campus. So I think if the university had $2 million, the very first thing to do is to establish a campus that is not here or is not far away, but it's a campus where both companies and startups can have a common ground, common shop, provide services, like machine shops, maker spaces. That's been done before. There's nothing new here. Cortex does that, right? So there's not a Cortex equivalent to science and engineering that I know of, and I think that would be the best use of the money that I know of, coming from the company perspective, right? And I get asked that question before, and people are like, hey, you guys are greedy, you're making a lot of money in profits and stuff. Well, then you use it to develop R&D. I say, well, because that's not our job. Private sector job is to take something and to make it into a product, right? The job of academia and government is to take the high risk, right, and develop the basic R&D that eventually connects to a product that people care about. And this is controversial for some people, so I apologize if this offends somebody here, but what I think is that, in my company, our motto is, what matters to us is not scientific discoveries in the lab or papers in Science and Nature. What matters to us is the technology that people, government, and companies use every day. The technologies that create value for people every single day. And that doesn't diminish the value that I put in R&D. I was a basic researcher for half my life, but I think there is a place and space for all of that. And I think this university in particular has a R&D engine that is second to none in this continent. And I think there is more to be done with it than just sending kids to work for Boeing. Apologies if somebody here loves Boeing and works for Boeing or is from Boeing. I think there is other companies that can harness the talent from here, or just seeing the guys going, elsewhere in the world to create value somewhere else. I think and I'm actually actively working with some of you here, I'm trying to find a way to really harness that connection. So yeah, if you convince the powers in place to shell out $20 million, I think we can return those $20 million to WashU in the region very quickly. Yeah.
A question, maybe particularly for your business, looking at the various gadgets that you were showing us along here, they all seem very sort of bespoke, like very particular purposes. Is there a market for these, or are you have a whole bunch of customers lined up for them, or is this supported? Are you primarily supported by grants, SBIRs, and so forth? Just kind of curious about the business model, how this works.
Yeah, great question. So our business model is pretty simple and complicated in a way. What we care about is we want to help reduce climate change by exploring space. So there's a reason for that. It's not too crazy when you think about it. So we know NASA very well. I was working at NASA, so that's kind of why we started. We know that NASA likes to take risk in technology. NSF does as well to an extent. The DOE does as well. But NASA in particular is believe it or not, is risk friendly for some things, and they have a lot of money, right? So we found that the place for us to invent these new gizmos, new architectures, bespoke technologies, that's the right word for that, is with a customer that has deep pockets and is not afraid of taking risk. So we found that NASA, being our customer number one, validates the technology, takes technical risk out of the equation, so that we can now go to other customers, right, in other fields, like industry, that are more traditionally risk averse and definitely run away when you say to them, hey, we do hardware, right, because a lot of money. That's helping us really develop the fundamental platform technologies that you see before. All of this, you see different shapes and that, but under the hood, it's all the same thing. It's all these adaptive optics platform technologies that really allow us to leverage the physical phenomenon that we all have discovered in school and now use industrially. So I think that's, for us, it's been finding the one customer, and this is probably, if you're thinking about a startup, or you join a startup, or you have one already, is get your customer number one line up and use that to build credibility with customer number 2, 3, 4, N. And that's how the business model works for us, is NASA's number one, de-risk technology, find customer 2, 3, 4, 5. which in a way, in academia, by writing papers, that's how you de-risk the technology, right? Or your idea. You just publish your idea, get reviewed by your colleagues, get credibility, and then you go get the big grant. So it's really the same process applies, right? So it's just in a different scale. Yeah.
You mentioned climate change twice now, but you also talked about mining the seafloor and mining the moon. And I don't see how any of this technology presented, which all seems cool. I mean, that's all great. Like, how does that actually circle back to combating climate change problems here?
Fantastic question. So all the stuff that Tesla needs to build batteries, all the stuff that wind turbine builders need to build the next blades and the magnets to make that conversion, solar cells, all those rare earths, critical minerals, we have very few of those on land. Most of that is on the seafloor. So a way to decarbonize industry on land is to mine the seafloor. Now there is a risk there. You see how we mine on land. It's very far from sustainability. So the reason why we're pushing this technology hard is because we can actually, at the same time we can find these minerals, we can find habitats in which they coexist. And what we're working on with the USGS and the Department of Interior is to basically find these ecosystems and make national parks on the seafloor. Make places where we should not extract resources, and only extract resources in the places that we know there is lower impact. There's never going to be zero impact in mining, but they can be lower impact and they can be sustainably done longer term. And that's as far as the ocean. The moon, well, arguably the moon is a dead rock, but it has resources like rare earths as well, and perhaps helium-3, although that's also controversial. How can that be used to do fusion energy? But there are resources there that can help combat climate change back on Earth as well. For one, you can build rockets on the moon. Use hydrogen from the regolith to propel your rockets without burning anything from Earth. So it's cheaper once you can build that infrastructure, and it's clean propulsion as well.
So it's a strategic impact on climate change, less tactical.
Yeah, yes. It's a great question. I think, thank you for bringing it up. There's a question behind you. Check.
Yeah, I was, so other than, I guess, Tesla and mining companies, are there other industrial sectors you plan on targeting with these technologies after they've been proven by your NASA funding?
Yeah, so one actually close to heart here in St. Louis. So if you are a farmer now, the better way to make money is to not farm. And the reason why is, farming is a very carbon intensive and activity. Fertilizers, making ammonia, it's pretty energy intensive. Moving Earth day and night, releases carbon in the atmosphere pretty massively. Chemicals, pesticides. So the carbon cap and trade market that is today enables farmers that want to stop farming, or at least use more sustainably farming techniques that are more expensive, but they can capture some of the offsets from carbon. They can essentially get paid, right, for every measure of carbon that is sequestered and trapped on the ground and not released. So our sensors now can, we believe for the first time, and that's what Benson Hill, Bayer, and other big ag companies believe as well, is that we can actually measure precisely the amount of carbon that is not being released when you apply these new farming techniques or when you stop farming altogether. So it's a way for farmers to really go into the insurance company or to the market and say, hey, this is how much carbon I'm keeping here, pay me accordingly, right? And I think that's one of the examples of how these tools help environment. The other one is this LiDAR constellation thing that is a bit more futuristic, but what we're doing is, we're basically, if it works, again, enabling a service that can provide global permanent coverage to measure these climate change indicators, which can be used to A, make policy, and B, assess whether something is happening and something is working or not when you implement it. So, yeah. And all of this thanks to NASA, who have thought, right? So, but I think, just to maybe wrap up, Eric, I think one of the things that makes me most happy to really be back here is, today I got a chance to see a new lab downstairs. What is your lab? Yeah. So see the new generation of sensors that today are the size of a room or the basement. This is when I was in grad school. That was the Raman instrument, state of the art. It was the size of your basement, and I was using that for my PhD research 18 years ago. And today we have Raman systems the size of this calculator, right? So what makes me happy is that there is this high-end research being done here, of course everywhere, but here particularly, that I'm hoping that one day we transform it into something that is as small and as useful as what we've done with other laser techniques. So it's been really, really a phenomenal day for me. So hopefully some of you learned something today. If not, I apologize. But yeah, you have again my contact email. You can complain or you can send me some more information. And our lab is in South City, so you're welcome to stop by and hopefully we see each other again. So yeah.
All right. Thank you.